In these videos we are going to introduce the concept of subgroups, but I would like to give you some intuition here first. So I choose this example of Z4 under addition, so that would be the set 0, 1, 2, 3, and your group is here, right? So this is a group under addition because it is the operation is associative, right? You can pick any of these elements and add them in any order you want. Okay, so these are the axioms for a group, right? 2. There is an identity. Well, yes, 0. If you add 0 to any other element, let us take 1 for instance, you get 1 plus 0, you get 1, so this is the identity. Okay, there is an identity. You can do this to any other element. And the third axiom is the existence of inverses for every element. Okay, let us pick one element, like for instance 3. What is the inverse of 3? Well, if you add 3 to 1, 3 plus 1 modulo 4, you get 0, right? And 0 is the identity. Okay, well, the identity here is 0, right? So you can check that all the elements have inverses, so this is a group, right? Z4 under the operation plus is closed for the operation and is a group under this operation. Now, what if I take a set with only these elements 0 and 2, and I keep the same operation, modulo 4? Okay, so I take a subset, because 0, 2 is a subset of this Z4, right? So I take a subset and I take the same operation. My question is, the group axioms are going to be still valid only on this small subset under the same operation? Well, let us check if it is, if you can associate. Well, definitely you can, right? If you associate 0 plus 2 in any order plus 0 in any order, it will always be associative, right? Okay, do I have an identity? Well, I do, because the identity of Z4 is here in this set. The identity of Z4 is 0 and 0 is here. Okay, so this is the Z4 identity, right? Okay, so we do have the identity. You can check that 0 is the identity, because 0 plus 2 equals 2. So you perform the operation with the identity and the elements stay the same, so this is the identity. Okay, what about inverses? Well, 0 is the inverse of itself, because if I add 0 to 0, I get 0, and 0 is the identity. And 2, if I add 2 plus 2, I get 0, and 0 is the identity. So 2 is the inverse of itself. So in this small subset, in this subset of Z4, all the group axioms are valid too. So because the operation is associative here, the operation is associative. There is the identity. The identity is 0. So the identity, this set took the identity from Z4, the same identity as the group, and every single element has an inverse too. Okay, what shall we call to this subset of the set of the group under the same operation where the group axioms are valid? Well, that's exactly what we call a subgroup. Okay, and so now we introduce the concept of a subgroup. Okay. If a subset H of a group G is itself a group, like we saw in the previous example, under the same operation of G, we say H is a subgroup of G. Now, usually we write it this way: H is a subgroup of G. Okay, means H is a subgroup of G. Now, a set is a subset of itself. Okay, so H can be equal to G here. Okay, if you're considering a set that is a proper subset of G, meaning that H is not equal to G, so we say H is a subgroup of G, and we write this way. Okay, this one is called a proper subgroup. Proper subgroup. Okay. For instance, if you can check that. If you take only the element identity, this is called the trivial subgroup of G. Okay. All the others that are not only the identity, they are called the non-trivial subgroups of G. Check that Zn is not a subgroup of Z. Okay, because Zn is addition module n. So this is not a subgroup of Z under addition. Okay, since addition module n is not the operation of Z. Okay. Another aspect of notation is if you have a group set with an operation addition, and this is a group, and you have another set under the operation multiplication, algebraists usually denote the identity here would be 0, right? And the identity here would be 1. Okay, so frequently algebraists use this symbol 0 to denote the additive identity element, and the symbol 1 to denote a multiplicative identity element, even if they may not be actually denoting the integers 0 and 1. You see, like for instance, if your set are matrices, you see, under addition, for instance, in the space of 2 by 2 matrices, okay, so under addition your identity would be 0, 0, 0, 0, okay, and algebraists they call it this 0. Okay, so this might not be number 0, but the additive, okay, the additive identity. Now you can check if the positive rational numbers under multiplication, if that is a subgroup of the positive reals under multiplication. Think about it and check it. You will see that yes, this is true. Talking about groups of order 4, there are two different types of group structures of order 4. These unities the 1i minus 1 minus I, we call this the Klein-Vier-group, and we usually write this with a V because in German we write vier. Vier is 4 in German, okay? And the other group structure of order 4 is Z4, okay? Since I did not introduce certain group theory concepts here, I'm going to show you this through the Cayley tables, okay? So on the left you have the Z4 Cayley table. Do not forget this is addition module 4. Looking at the Cayley table, you can see that this is a group, right? And this is a sort of structure, and this is on the left, and on the right you have the Klein-Vier group, the Klein-Vier group. Under this Cayley table. Now we should try to find subgroups here. And we are going to make a subgroup diagram for Z4 and a subgroup diagram for the Klein-Vier group. So Z4, the only proper subgroup of Z4 is the set Z2, because this one is the improper subgroup of Z4, okay? And this is the diagram, the subgroup diagrams of the Vier-Klein group, where these three, EA, EB, and the identity and C, there are three non-trivial subgroups of the Klein-Vier group, and the identity is the trivial subgroup. So here you have a subgroup diagram. This is very important. You should do this to other groups, okay?